So in the second part of this morning about the basics of stellar evolution theory, we will think about how the actual star will behave based on the basic equations and equation of states we discussed in the previous lecture. So yeah, the same thing is written here. Yeah, based on the basic physics in the previous lecture, we consider how stars change over time, and we focus on the evolution at the center, and also, we think separately the evolution of the center. At first, we discuss how the star will change at the center, and then we see how the star will change at the surface. So let's think about how the star will change itself at the center. So for that, to think about that, we are going to discuss in this plane. This is the density and this is the temperature. And we are first going to characterize this plane. What do we mean by characterizing? So let's say we derive the equation of states for ideal gas and also the degenerate pressure. Let's think about where this pressure will be dominating in this plane. There should be somewhere these two pressure gets similar. So let's think where these two pressure gets similar, and we should be able to draw a line in this plane where these two pressures gets similar, and that's if we do simple exercise, and then we basically get this line should be proportional to the density of the 2/3, and there's some constant, of course. And if you put the proper constant, and then you get this line here, which gives you where the gas pressure and electron degenerate pressure gets similar. So above this line, the ideal gas pressure will be dominating. Below this line, for the higher density cases, this region, the degenerate pressure should be dominating the equation of state. We can do the same exercise for the different equation of states. Sorry. So in this case, we now think of degenerate pressure, and there's a electron degenerate pressure. And as we briefly talked about this, but when those two pressures get similar is where these two transitions should occur. And basically, if we equate, then we get some density. So this line is just a constant. And as we were talking before, this is 10 to the 6 gram per cubic centimeter, and so there should be some line where there's a density where non-relativistic, where the transition from relativistic to non-relativistic equation of states should happen in this plane. We can, of course, do the same exercise for the relativistic degenerate gas and relativistic degenerate pressure and the usual ideal gas pressure. And then we get the temperature should be proportional to rho to the 1/3, and that will be dominating here. So here is basically where the ideal gas pressure and the relativistic electron gas pressure will be kind of similar. What's left? So we have the radiation pressure, and we are going to think about the radiation, where radiation pressure and the ideal gas pressure gets similar. And then what we get is this, again, this similar equation to the relativistic degenerate gas cases. But anyway, we get this, and of course we have different constant. So we have another line here. And that's basically it. So radiation pressure and degenerate pressure will not be touched. So this, remember, this was tend to be these had the same gradient. So these two lines just go parallelly. So radiation pressure, we don't need to think about these degenerate pressure and radiation pressure combination. So this is basically what we get when we think about those equation of states we considered in the previous lecture. So there will be a line where here the radiation pressure will be dominating the pressure, and there's some pressure which is proportional to rho to the 1/3, and below that line, ideal gas will be dominating the pressure. And then as the density goes higher, then at some point the degenerate pressure should be playing a role. And then, so here there's a region where non-relativistic degenerate pressure will be dominating. And then from some constant density, which is 10 to the 6 gram per cc, the non-relativistic relativistic electron gas pressure should be dominating in this region. So we can characterize we have characterized this plane of the rho c and the central, central density and central temperature. And the question is where, of course, let's use this to consider the actual star. And as we did in the last part of the previous lecture, if we use this equation of motion, we can do a very simplified way of deriving this or solving this equation. And the central pressure is basically proportional to this value if you take this. And so, but here we use the central average density. But let's say, we can show that the average density is that central density is proportional to the average density. So we just simply change this average density here to the central density, and that's what the star is supposed to, follow. And if we now think that let's assume the central pressure at the center of the star, the ideal gas pressure is dominating. So then this central pressure of the gas should be written in this way. Then what we get is that central density of a star should be just putting this to here, and then we have this correlation. So we can write this in this way. And so central density should be proportional to T central temperature to the cube divided by mass of mass squared. Or, this equation can be written in terms of T, and then these two equations is basically the same. But what we saw here, so let's get back to this the same diagram. This is central density of a star, and this is central temperature of a star. And before we at the beginning we characterized where these equation of states will change, and we now found that in the center of the star, if the equation of state is dominated by gas pressure, then central temperature should be proportional to mass to 2/3 and density to 1/3. What does it mean? So here's a point for sun, which I will give you. And so this is actual point from the sun. So once the mass is fixed in a star, then temperature should be proportional to 1/3 of the density. So that means this sun can only move this line in this plane in this entire, sun are only allowed to move in this line. That's what physics tell you. And so the evolution at the center of the sun, as time goes, the density gets higher. But how it's reacting is that density gets higher, but the central density cannot go like this or like this. It must follow this line, and the center of the sun will evolve in this way towards this line. So that's how the sun is supposed to evolve. So here was the sun, and it's the same diagram. And as I said, the sun can only move in this way here in this ideal gas pressure dominated region. So it goes like this. This is the 1 solar mass line. And if we put a different mass, so this central density is for given temperature, the density is inversely proportional to mass squared. So that means the density gets smaller and smaller as the mass increases for a given temperature. So that means in this diagram, the higher mass star still follow the same equation, T proportional to density to 1/3, but the line will get higher as the mass of the star increases. And let's say 10 solar mass star can only move in this line. And of course, evolution occurs from the low density to high density. So the evolution of 10 solar masses starts from this side and then climbs up to this the other end of this diagram. So that's how the center of the star should change. This is basically determined by the equation of motion and also the ideal gas pressure we derived in the previous lecture. So it maybe sounds a bit weird as the mass gets higher, the central density should get lower. So that's how the star governed by the ideal gas pressure equation of state will react. And of course, instead of the density, you get much higher temperature. So that's how you can still keep the massive, the higher mass of the mass of the star. And in case of 1 solar masses, then as you climb up this, as it evolves, as it climbs up this line, then you start to get close to this line of degenerate pressure and ideal gas pressure. What does it mean? So it was if the gas is only dominated by the ideal gas pressure, then it should go up like this. But then as the gas pressure, effect of the gas pressure decreases, then this deviates from the line you are supposed to climb with the ideal gas pressure, and then it goes to the case of degenerate pressure. So in the case of the relativistic, non-relativistic degenerate pressure, we saw in the previous lecture that central density is proportional to mass. So only mass will determine where the central density is, and that's basically, so it doesn't, temperature doesn't play a role. So let's say this is 1 solar mass. So this is the constant line for 1 solar mass and 0.1 solar mass star, which is dominated by this degenerate gas. So as the degenerate pressure goes into effect, this line will transit to this just constant density line, which is between this way. So 1 solar mass star, currently it's dominated by gas pressure, but as it evolves, this sun start to hit the region where the degenerate gas pressure kicks in, and that will, degenerate gas pressure will take over this pressure, and then in the end, degenerate pressure will be dominating the way the star is supported, and then that will be it will just cool down as shown as a constant density star at the center. And the lower mass star does the same thing basically. So it's eventually until some pressure, until some mass, this lower mass star must hit this region, because the star must follow this equation. So 1 solar mass star cannot go this way or that way. This will eventually must hit this degenerate pressure region. So that this low mass star will be eventually supported by degenerate pressure, and that's unavoidable. But if the mass is sufficiently high, then you will avoid this region of degenerate pressure. And remember, this gradient was T to T. So sorry. This was T to the rho 1/3, which is basically the same as this where this line of stars. So this will never, and also this line is also the same gradient. So this line will never touch this region. So if the mass is sufficiently high, then this will just keep climbing without any effect from the degenerate pressure. And 100 solar masses, it's of course much farther away from this degenerate gas region, but it gets closer to this radiation pressure dominated region. So that's how, just from the equation of state and the equation of motion, you can already see how the center of the star should be evolving as time, as the density gets higher, and what is the fate of the star can be seen in this simple diagram. Yes?
I would like, because this behavior, what you have said, everything is correct, of course. And we can put everything. The equations show that the evolution will go in this way, right? We'll see it later on, probably detailed calculations.
Yes.
But to see why the temperature behaves in this way, we can make a very simple trick, just to show you how, and you will get flavor why things go like this. You write down very simple thing. The central, first we use, of course, hydrostatic equilibrium tells us that we have this relation between central density and mass and central pressure, right? Power 1/3, right? Oh, 4/3. Like this.
Mm-hmm.
Oh, sorry. Yes, so the central temperature is what? Then we can imagine that the star consists of a mixture of non-degenerate and degenerate gas. Then you can write down that the central pressure would be central temperature, right? Multiplied by central pressure. Plus non-degenerate K2, you call this K2 constant, right? Rho central to the power 5/3, right?
Mm-hmm.
And you put here, you combine these equations, and from these two equations, you find that the central temperature, divide everything by density, and you see that this is a combination of this term, hydrostatic equilibrium, to the power 1/3, minus K2 2/3. And if you plot this function, logarithm temperature, as a function of logarithm pressure, this term first dominates. Then this term comes into play at high densities in the non-relativistic limit. So this is why the behavior goes like this. So this explains this. So this means that at high densities, this term becomes more and more important. And this is always hold because this is hydrostatic equilibrium term. And this term comes from the equation of state.
Yep.
And this is why the temperature, because the temperature is the signature of non-degenerate matter, right?
Mm-hmm.
We don't speak about temperature of degenerate electrons, basically. Only in some special cases, so in solid state physics, etc., etc. But here, this equation just shows you that the temperature must drop after some point. And if you make a simple exercise, if you put here a relativistic term, you will see something else. You can do it yourself. Okay, sorry.
No, thank you very much.
But this gives just
Yeah.
simple
Yes.
explanation.
How does it behave in this way? Yeah. Thank you. So yes. So this was it, and that's how this star is changing itself at the center. And of course, we can put many more information. This will be where nuclear burning should occur or should start, and this will be discussed tomorrow. And so this is basically from here, hydrogen should start to burn, and then this is where helium should start burn, and so on, which we'll see tomorrow. And also, we can put where the star will be unstable in this diagram. This will be the topic of the exercise in this afternoon. If we combine everything, we can put in something like this, and we can already start to see the fate of stars in this diagram. As I said, so the fate of the mass, fate of a star is just determined by the mass. And of course, assuming the composition is the same and so on. But basically, because the line in this central region of the diagram is just determined by the mass. And if the mass is given, then the star can only move in a certain line in this diagram. And if the mass is small, then as we saw, you will eventually hit this degenerate region, and this change to the degenerate pressure-dominated star is unavoidable. If the mass is sufficiently high, then you can avoid this degenerate region, and then the star can go all the way to here. But at this top region, there's a region where the star will collapse, basically. And that will lead to a supernova explosion, as we will see in the afternoon. And other interesting result is if the mass is very extremely high, then there's a region of the instability here, and star can enter this another region, and which can cause another fate of the star, which is going to be discussed in this Friday. So this is basically summarizing how the star should change itself, or how the star evolution will happen at the center, and why the star's fate is determined just by mass, and that's basically determined in this diagram. And of course, this was very idealized way. We can do a very sophisticated or proper star evolution calculation. And these lines are what you get by actually numerically calculating the star evolution. This lower line is for 15 solar masses, and the upper line is 25 solar masses. And what our theory told us is the star, for given mass, the star should follow this line. And overall, this is correct, and this the star is following this low temperature proportional to rho 1/3. But of course, it has very more sophisticated behavior. And also, at first, it follows very relatively well, but in the end, it starts to deviate a lot. This is due to the neutrino emission from the star, which takes, so when the star gets the central region of the star gets extremely high temperature, there will be thermal neutrinos emitted from the central region of the star that can basically take the energy away from the star, and the equation of state will not totally follow what you expect from the ideal gas pressure. That it gets much cooler easily, so that makes more degenerate deviation from this expected line a lot in the higher density region. But overall, this simple theory is basically explaining this overall behavior of the stars. So that was about how the star evolves at the center, and we move on to how the star looks like at the surface. And of course, how the star will change at the surface is extremely important, because how we observe star at the surface, and it's basically almost impossible to see what's happening at the center. So we need to think about what's going on at the surface. And to summarize, this is how it behaves, and we try to understand those. And this is the surface temperature of the star, and this is the luminosity of the star. Each line shows the one, so this is 6 solar mass star, how will it change, and this is 8 solar mass, 10, 12, 16, and 20 solar mass star, how it will change. And the star, basically the star, so this line is this end of the line is where hydrogen is ignited, and we call this zero-age main sequence. Basically, this is main sequence where the hydrogen has just started to burn. So this end is called zero-age main sequence. And then as time goes, then the star moves in this way, and then collapses as the star will collapse at the other end of this line. So this is basic behavior of the star at the surface. And let's see how it actually changes over time. So I will show you the actual evolution of the star as a movie in this here. So this is, we will see the surface behavior here. This is effective temperature, and this is the luminosity of a star. And this is the central density and central temperature of a star, which we have discussed so far. And this line is where basically the degenerate pressure dominates, and there's another line where the gas pressure, the radiation pressure and gas pressure deviation is. And there's several lines where, like this is where helium burning starts, and this is another, it's hard to see, but this line basically indicates where the next stage of burning should start. And here is a line, and this end is the center of the star. So this, the behavior of this at the center we have discussed, and then the other end is the surface of the star. And then there's of course, it should be connected continuously, and this is in the star inside the density and temperature inside the star. And this is, I'm showing the 25 solar mass star evolution without mass loss for simplicity. And this is the composition or abundance of the star inside. At first, this is already like 100 years after the beginning, but at first, there's basically, it's composed of hydrogen and helium. This is solar mass, solar composition. There's already some changes, but this is because this is already 100 years after the beginning. But anyway, basically nothing happened, and mostly hydrogen and helium are dominating. And we can see how the star will evolve. Yeah, that was it. So let's see what happened. So oops. So at first, let me, yes, yes. So at first, at the center, the hydrogen is burning, as you can see from here. So it's the center, the hydrogen is burning, and it stays there. The center region stays there for a while. And this is the fraction of hydrogen, and it continues to go down. And then, so during the hydrogen burning, the star basically keeps slightly expanding. And then at some point, this star will go in a different way. So it starts to contract. So this is T effective and luminosity, and you can, this is 4 pi r squared sigma t to the fourth. So you can imagine the radius gets higher as you go in this direction. So it basically, at some point, this star is start to contract, and that's basically because the nuclear energy supply. So that happens when the most of the hydrogen gets is used. So you can see this is the hydrogen fraction, and you can see this contraction is happening when the hydrogen is mostly disappearing in the star. So basically, the star is no longer having enough nuclear energy to support this configuration from the hydrogen burning, and that's why it starts to contract. And then at some point it starts to expand, and that I will come back to later why this is happening. But it starts to expand as the hydrogen burning stops at the center, and then goes to basically it gets expanding, and then gets to this end, the other end of the lower temperature end, and then basically the rest of the life will be spent here, and then at the center it just continue to go up and up. The density gets higher and higher, and temperature gets higher and higher. And as time goes, so this different material will be burnt, and at the center now its oxygen is dominating. All the helium is almost burnt, and then now oxygen is dominating. And then as it goes, oxygen will be burnt again. So oxygen at the center is lost, and then another elements are coming. And then it goes until iron core is formed. And then in the end, it will be, the star is just start to collapse. And the end point of this calculation is when the star starts to collapse. So that was the movie. Okay.
Takashi,
yes.
Does this simulation account for some convention model?
Could you say it again?
Does this simulation account for some convention model?
Convention.
Or without convention?
Convection. Convection. Or convection. Yes, this takes into account convection. So this blue region is where convection is dominating, the energy transport, and this green line, where green line is where the radiation energy transport is dominating. So you can see the difference in the energy transport in this difference in the color. And yeah, I should have already, and also this red is basically where the energy generation is happening, so where the nuclear burning is happening, basically. So you can see again the movie with that. So at first, there's a center region, it goes quickly, but center region was convective and the surface was radiative. But as it expands, the surface region will be mostly convective, and then at the center will be mostly radiating, and then of course there will be more complication there.
Can you once again explain this change of the behavior, decreasing and increasing?
Yes, I will go. Let's move on to that. So this is the diagram, or my close-up view of this change, and here is the radius is written, and then this is the age divided by 10 to the 6 years. And yeah, at first this is where the hydrogen is started to burn, and that we call zero age main sequence. And so as it evolves, basically the radius gets slightly higher, but yes. And then when there is no sufficiently hydrogen burning to support the star will start to contract. And at some moment, so are you asking why the star is going to contract or afterwards? After the expansion, yes. So what happens here? So it basically star basically starts to contract because of the lack of the the nuclear energy. But at some point, this will start to expand. The reason is that so at the center, and this is where the basically hydrogen burning phase will finish, and that we call terminal age main sequence. And the reason is that so there's a hydrogen. So this reason is I think nobody knows exactly why, but there's many different ways of think about this. And the one way is that there's helium core because hydrogen is exhausted, and on top of that there's a hydrogen-rich envelope. So this is where hydrogen is. And at the center now, the hydrogen is no longer exist, and all the star is basically at first it starts to contract. But at some point, this at the boundary between helium-rich core, helium core, and the surface, the hydrogen-rich core, the temperature gets high enough so that the hydrogen this interface between the helium core and the hydrogen-rich envelope will start to burn. So nuclear reaction, at first the nuclear reaction was only happening at the center of the star, but when it contracts, at some point this shell above the helium core will start to burn. So there will be hydrogen shell burning is happening. And when this shell is formed, then let's imagine there's some shell burning, the burning shell. So if this shell it contracts, then that means temperature gets higher. And then when the nuclear burning is happening, when the temperature gets higher, this nuclear burning gets more efficient because the nuclear burning, the rate of the energy release from the nuclear burning is proportional to temperature to the force or even more. So what happens is when this contraction high temperature gets higher, then this shell, since this temperature gets higher, the nuclear reaction rate gets higher, the more energy is released. So it wants to expand instead of the contraction. Yes?
Helium is burning now?
No, not yet. So this is still helium is, so at the surface hydrogen is burning. So helium is not yet, the temperature is not high enough to burn the helium. But the temperature can get high enough to burn this hydrogen shell around the helium core. Then this shell basically doesn't want to move its position, but of course central region where the helium burning is not yet ignited, this central region wants to contract more. And then what happens is that to keep the pressure here, so this region want to stay in a certain radius because of the nuclear burning, but central region wants to go down. And then what happens is this pressure here will be very small because this region is just staying there. And then if the outer region gets also keep contracting, then the pressure here will be also too high. So what happens is because of this shell formation, the star, to keep this this configuration, the outer layer, so to keep the pressure there kind of small, the outer region of the star needs to expand, and that's why this star is turns from the contraction to expansion at the surface. So basically what's, yeah, I wrote in very like exaggerated way, but yeah, this central core is only like 0.1 or 0.1 solar radius, while the outer radius can be 1,000 of the stellar radius. So this star needs to expand really a lot. So that's what's happening. So here, the reason why the contraction stops and starts to expand is the hydrogen at the border between helium core and the hydrogen-rich envelope is started to burn, and that makes the outer layer of the star to expand to keep the hydrostatic structure. So that's basically what we see in general in the stellar structure or stellar evolution theory. What we see, what we can call Miller principle, is that when there's a kind of shell burning region in a star, then when there's this shell burning, when the center of this shell tries to contract, then the surface will try to expand. It's like this burning shell behave like a mirror. So some people call this is Miller principle. So if there's a shell and if the core is contracting, then the surface will expand. And then opposite is also true. If there's a shell burning and if the core is trying to expand, then the surface of the star tries to be smaller to react to this reaction. So that is basically caused by this shell burning, nuclear burning happening not at the center, but the shell surrounding the core. Yes.
First of all, I would draw attention of the listeners to the very short time of the expansion. If you go
yes.
Here, see how rapidly star passes from the matrices in the terms of terminating matrices to the beginning of the red giant branch. This time is basically thermal time scale of the shell. So the adjustment to the new configuration occurs very rapidly. This is why we don't observe these stars here in the first contrast hierarchy, because the stars pass very rapidly from main systems to the giant branch. So so-called together, right? And this is very important to realize. And the second point is, if you look at the evolutionary tracks, you showed us the first contraction diagram in very a lot of, no, previous. Yes, here. You may notice that there is a sort of boundary at 3.5 thousand Kelvin with the effective temperature of the star, and no star can cross this boundary. And for those who know the answer, don't tell the listener the answer so far. But I would ask the students to think about this. Why the star can't go to cooler region? For example, we don't observe the stars during the evolution, after the main sequence, which crosses this boundary. This is the Hayashi, right? And for those who don't know answer, please think about this. This is a very nice explanation, physically very deep, and I give some hints. It relates to the equation of space of the gas, which moves up during this expansion.
Okay, thank you. So yes, so as already explained, so there was a contraction, and then it goes that this moves star expands really quickly. So as I said, this is the the age of the star, and to get here from the beginning it took 6 million years, and then from here to there it's like 0.4 million years, and from here to there it was very small time scale. Then it stops going farther away, which I shouldn't explain here because you need to think about that. So I won't explain that, but then the star cannot go much farther away, lower temperature. So what the star does is basically start to climb something called Hayashi line, and the rest of the life will be spent around here just with the huge envelope, and then this is the end point of the surface evolution of the star, but the core continues to evolve, and the star will collapse and explode at this end. And another way to see this evolution is, so there was a question about the convection, and this is the time, the age of the star, and this is the mass coordinate. So this is the center of the star, and this is the surface of the star. This is an example of 25 solar masses, and in this model we are thinking about the mass loss, so the mass is going to change. But anyway, at first, so this is where the hydrogen burning, this is zero-age main sequence, and so when the hydrogen starts to burn, and where this hatch is basically shows where the convection is happening, where the mixing of the material by the motion of the material we discussed before is happening. So at the surface, most of the energy transfer is done by radiation. So at the surface, it's radiation radiation is doing the energy transfer, and at the center there's a convection during the hydrogen burning. And then as the star expands, then the surface layer will be convective, and then there will be helium burning region here. So note that this is in logarithmic time scale, so most of the stellar life is just dominated by the hydrogen burning phase, and then helium burns, and then I will come back to mass loss, but many of the mass is lost during this phase where the temperature is low, and this will just continue to the end. So now we are only seeing, so this we only are going to see where below 10 solar masses. This is 10 now, and then at the end, let's say 1 year before the explosion, this convection is caused by the neon burning, and then several months before several months before the explosion, oxygen at the center will start to burn, and you can see still the surface is convective, but there's other convective region as well, and that's basically caused by the shell burning. As I said before, there's some regions can burn in the shell, and then in the end there's a silicon burning, and then star will just collapse. And in the end, this is how the star looks like in a simplified picture. In the end, there's an iron core, and that leads to the collapse, and then there's a silicon burning region, and then there's a silicon rich region where the temperature is not high enough to burn silicon, and then there should be a boundary between silicon rich region and oxygen rich region, and then at the boundary, the temperature may be high enough to burn the oxygen, not the silicon, but the oxygen could be burnt at this boundary, and that is causing this this convection. Well, I mean, these convection are coming from the shell burning, and that continues, and then we have the hydrogen-rich envelope at the surface, and this is basically the final structure of massive star. So far we didn't think about the mass loss much, but here we are focusing on the especially massive star, which will end up with supernovae. And the massive stars basically means that their luminosity is higher. And if the luminosity is high, then there will be a lot of radiation pressure at the surface of the star. And that radiation pressure can push the material at the surface of the star, and the star can keep losing its mass because of this radiation pressure at the surface. And we do observe massive stars losing its mass, and this is one example of Wolf-Rayet star. And this is the star, and this star is surrounded by this material lost by this this star, and we can observe many stars losing its mass. I mean, especially massive stars losing its mass. And this is kind of summary of the mass loss rate. So this is the luminosity of a star, and this is the mass loss rate you kind of from basically what we observe, mass loss rate we observe, and some theories are also there, but the mass loss rate, expected mass loss rate. So in the main sequence, so this is only luminosity, but of course temperature can be different, and the hot stars, which is at the main sequence, is expected to lose this mass loss rate is expected to be something like this. And as the temperature gets cooler and goes to the red supergiant, so goes to goes to this region, then mass loss rate can get something like here. So basically, when the star gets cooler, the mass loss rate can increase, and then that can lead to a lot of mass loss. So that we already see in this stellar evolution actually. So up to 25 solar masses, so the star starts to die here and then evolves, and then start to evolve from here and then dies at the other end. But then from around, let's say this 30 solar mass star, it starts to do the same thing as the lower mass star, but then it turns to this side. So this side is much hotter temperature, and as you can see from this equation, luminosity is not changing much, but temperature gets much higher, which means the radius is getting very close, small. So what is causing this is the mass loss. So until about 25 solar masses, the star will not lose a lot of mass, and it can keep the hydrogen-rich envelope until the end of the life, and that will that's why the star will end up and collapse at the red supergiant stage. But if the mass is large enough, then this mass loss rate gets extremely high, so that the hydrogen-rich envelope, hydrogen in the star, will be lost entirely. And then what happens is that because of this lost hydrogen star, because of the loss of this hydrogen envelope, we basically start to see helium layer, and that will shrink the star, and the star will be something called Wolf-Rayet star. So basically only helium, no hydrogen is left in this star, and because of the mass loss, star comes to this end, and the star ends their lives in this region when the mass is large enough. So that's the reason that, especially for the high mass star, this mass loss gets important to understand the behavior of the star at the surface. So this is kind of summary of the final mass of the stars, and so this is the initial mass of the star, and this is the mass of the star at the end. So if there's no mass loss, and if the star keeps its mass from the original one, then the star must just lie in this region. But so as the mass gets higher, and so around 10 solar masses up to, let's say, 10 solar masses, this initial mass and the final mass is not, it's not so different. So there's not much mass loss is taking place because of the lower luminosity. But as the mass gets higher, then you see more mass is lost from the star because of the higher luminosity and higher mass loss rate. And up from some point, so as we saw in this diagram, around between 25 and 30 solar masses, the star loses a lot of mass, and basically loses all the hydrogen rich envelope it has. So from some point it loses a lot of mass, and then basically the star will end up will explode or die as a Wolf-Rayet star, stars without any hydrogen. And and then of course as the mass gets higher, then you lose more mass, and the final mass may be smaller. So basically that was the summary of the very simple summary of the stellar evolution. We started from the central evolution, and that must follow a certain track given by the mass, determined by the mass. And then at the surface, the star evolves from the zero-age main sequence. And then when the hydrogen is lost at the center, the star must expand because of the shell burning. And then if there's no mass loss, no significant mass loss, then the star will basically end up with this expanded will end its life as this big star called red supergiants. If the mass is sufficiently high, there's mass loss will play a significant role, and many mass will be lost, and all of the hydrogen-rich envelope will be lost, and then the star will end up with Wolf-Rayet stars. And of course, I showed you a very simplified picture of the stellar evolution, and I didn't take into account many other physics which can play a role and change how the star evolves. And one example, I will just go over some physics I didn't discuss. And the biggest one I think is probably the rotation. And I didn't talk about the rotation at all, but the rotation can change how the star evolves and behaves completely. And especially the biggest change you can expect is there will be extra mixing caused by the rotation. So, for example, meridional circulation, which can cause extra mixing. And what is this? So, if the star, when the star is rotating, of course, the shape of the star can be slightly deformed because of the centrifugal force. So, if you light in a very exaggerated way, then if there's no rotation, star is just sphere. And you know, if we assume spherical symmetry, temperature at the surface is everywhere is the same. But if there's a rotation, then because of the centrifugal force, the star shape should be a bit different. And of course, star won't be like this deformed. But you know, if you write in exaggerate, maybe I should do in a more mild way. But yeah, star should be, you know, if the star is rotating on this axis, then the shape won't be spherical, and there should be this star should be deformed because of the rotation. And what happens is that because of this deformation, this region, so roughly speaking, this equatorial, the temperature of the equator will be smaller than this pole region. So here there will be high temperature, and this at the equator the temperature will be slightly less than the equator, and that temperature difference of course can cause some instability or some kind of mixing in the star, which can cause some extra motion in the star. So if there's no rotation, probably at the center there will be convection and some material are mixed. But if there's a rapid rotation, there can be extra mixing by this caused by this kind of deformation by the centrifugal force, and that can give you some extra mixing, and that can affect the star evolution actually. Quite a lot. So this is some example of the difference caused by the rotation. And as we saw before, if there's no rotation, then the star will just at first it slightly expand and then contract and then it expands. But if there's a rapid rotation, what happens is that stars tries to be slightly more compact than those without rotation. This already has slight rotation, but if in the extreme case, the star will never expand. It just tries to contract. And the reason is that if the radiation, the rotation is rapid enough, then this rotational mixing at the surface and the convection mixing by convection can mix the whole entire star, and entire star behave like a single stellar core. So that means basically, so if there's no rotation, then only the central part of the star, the hydrogen at the central part of the star will be burned, and then there should be shell burning later on, which makes this expansion. But if entire star is mixed, then this whole the material of the hydrogen of the star is burned at the same time. So there won't be any shell, and whole the star is evolved like a core. So whole the star will directly change to helium-rich star. So the star will directly go to Wolf-Rayet star without any mass loss if the star is rapidly rotating. So that's one example of the quite different star evolution you get by this rapid rotation. And of course, the material is mixed more, so how the surface composition will be quite different, and how the star changes itself will also be dramatically changed by this rotation. Yes, so as I said, so the 20 solar mass star, if there's no rotation, it goes to, well, let's talk about 30 solar mass. So 30 solar mass star goes to there, and then in usual case, it goes there and then comes back to Wolf-Rayet star. But 30 solar mass star, if it's rotating very rapidly, then it can go directly to Wolf-Rayet star. And yeah, 20 solar mass star, it should, if there's no rotation, it should end its life at the red supergiant. But if it's rotating extremely rapidly, then it can directly go to the Wolf-Rayet star. And for example, in this case, it's from here to like 5.5 to 4.8. So it can go somewhere there directly. And if so, the evolution will be like this. And the Wolf-Rayet star can be directly made without any expansion.
We observe such stars.
There are several candidates, but of course it's very hard to confirm how the star, which way the star came. But if you see the Wolf-Rayet star, it may came from this way or this way. So it's hard to tell just by the observation. But there's several candidates which may went directly this way. So this was one example we didn't discuss, but can change the life of the star dramatically. And there's also many issues in the stellar evolution theory. So stellar evolution theory is kind of classic theory, which maybe some of you think this is basically completed and nothing can be done anymore, but which is not true. And there's several or many issues remains in the stellar evolution theory. And actually, even the main sequence, when the hydrogen is burning at the stellar center, this main sequence is also not understood or very well. So this is one example showing some inconsistency between theory and observation. So this is kind of an HR diagram, and this black contours shows the kind of number density of the stars dominating in this region. So there's many stars here, and not much stars in this region. And as was already explained, so most of the stellar life is spent during the main sequence. And once the stellar hydrogen at the center is burned, then the star quickly moves to this end, where, of course, you see many stars are sitting here at the red supergiant. So basically, star should this region is basically where the hydrogen should be burning, and then star moves to this end, and we shouldn't see much stars in between. So that's something you expect from the theory. But if you compare in detail, so this is one what the stellar evolution theory predicts. So this is from Geneva stellar track. So they predict the hydrogen starts to burn here. And as you can see, this end is kind of consistent with what we observe. But the other end, where the hydrogen stops burning, is basically here. So they predict the star should stop burning hydrogen at this region. But what we see is the stars are dominated up to there. So this theory is basically not predicting the star to go there, and it's basically there's some inconsistency between what the main sequence region we observe and what is predicted. And of course, this is one model. We can take another model. This is from based on the stellar evolution track from Bonn group in Germany. And they also make a good prediction for when the hydrogen starts to burn. But then again, this region where the burning ends is it's probably predicting slightly better than this one, but still it's not explaining the entirely where the hydrogen burning should end. And also, if you see at the top end, this region is kind of getting more bigger when the star gets close to this, when the star is very luminous, which means the star is close to the identical luminosity, and then somehow the star is expanding than the hydrogen burning stars are much more expanded than the theory predicts. So theory basically predicts something like this, but the difference between theory and the model gets much worse when the star is much more massive. So somehow stellar structure gets more expanded than we think when the mass is higher at the end of the hydrogen burning phase. So there's very many details which we cannot explain even during the main sequence. Yes?
What was the major difference
There's many difference. For one big difference is that where they adjust the parameter of the convection. So the reason why, part of the reason why this model gets better is that this mixing parameter for convection is calibrated here. Yes, so this is adjusted. This model is basically adjusted to match here. So that's why you can explain here. But of course, that parameter cannot explain there. So that means probably this convective parameter needs to be mass dependent. And in this model, this convection parameter is adjusted at the one solar mass. So that's why it's deviating more. So we are not saying which is better or not. So, but the way you treat the theory or you decide the parameter in theory is affecting this stellar evolution theory, and that is not as simple as what we assume now. And also another difference is this model tends to predict more expanded structure. So this is more compact than this model when it gets closer to the identical luminosity, and that's also coming from a difference in how they treat the convection. And that was during the main sequence where the hydrogen is burning, but also, so we don't understand very well even from the beginning, but at the end point is also very complicated. This doesn't look good, but let's say there's some supernova like 1987A, which is, I think you know this supernova very well, and this was a supernova at the LMC. And this was blue supergiant. And classical stellar evolution theory, so this star should be like around 20 or maybe slightly less, but the mass was around there. But in the standard evolution theory, the theory predicts star should end at the red supergiant. And nobody was expecting this star to explode here. And the big question is why this 87A, the progenitor, was there when it explodes. It doesn't make sense at all from the viewpoint of standard evolution theory. The star should explode at red supergiant. And we will come back to this on Friday. And yes, so this is one example. And now we have many progenitor detection, and we know many supernova explosions, supernova progenitors in a red supergiant, and that can explain that's what that's expected. But we see these are also another supernova progenitor so that one star exploded when it's there, and these greens are also kind of slightly bluer than, or temperature is higher than what the stellar evolution theory predicts, and there's also very massive stars which shouldn't explode there turned out to be exploding, and so on. So this standard stellar evolution theory is not also predicting that something is lacking there. That's clear, and we will discuss this on Friday, how you create these kind of weird supernova progenitors which cannot be explained by this standard stellar evolution theory. Basically, that was it. And yeah, we first started with how the star should change at the center. And that is basically determined once the mass is given, the fate of the star or the path the star can move is basically determined only by the mass. And that will determine how the central star should evolve. And we also saw how the star will change at the surface, and this formation of the shell was important in understanding this expansion. And you need to think about why stars stop expanding at this end. That's the food of thought for you. And I didn't, of course, this lecture was just for 3 hours. I couldn't discuss many important things, but one example was rotation, and many other physics should be actually taken into account, and that makes the modern stellar evolution theory. But even the latest stellar evolution theory, in which we take into account many the latest physics, there's many unsolved issues, like main sequence is not well understood, and many supernovae seems to be exploding, whereas stellar evolution theory I have discussed doesn't predict. Basically, that's it, and I will take the question.
May I ask you? As for the rotating star, can we use something like period theorem in rotation to understand the star is not explained?
So you mean?
We can write down sort of theory, period theorem for
yes.
rotation, right?
Yes.
So the sum can be kinetic plus gravitational plus rotational energy.
Yes.
Star. And can we use and the relation between them? For example, if we assume that star is rotating all the time at the rotational limit, then we have this sum of this energy must be equal to 0.
Yes.
Can this be used to understand that the star doesn't expand?
I don't.
I don't know the answer. I try to think see in non-rotating star, real theorem helps us to understand why the star gets expanded, for example,
so
and here, when you add the rotation.
Yeah, probably that can be done, but so
Let's see.
Yep. I don't know. I don't know. It's.
Rotation looks okay, then you have this exactly equal to 0.
Yes.
Critical rotation by definition makes all the energy, right? So in this case, but if the Kipling rotation doesn't tell you nothing about, it tells you about the relation between depths. Because the rotation is just according to this. Center of this. And what about radius? I can answer this.
Yeah, I cannot tell. Yeah, may be possible, but yeah, I'm not exactly sure. But let's think.
Because during the evolution, we know that the density must always increase.
Yes, yes.
And increasing density means increasing preparing velocity, right? If you consider the body rotation as
Yeah.
Yes. With constant mass, this means that the radius should contract.
Yes.
So maybe this means this.
Yeah. Yeah, probably that's.
Understand? What I'm saying. So Keplerian velocity is just all around the square. And this is just square root of density, right? This is Keplerian velocity. If this is almost constant, means that, but if the density, if suppose it's not constant, not like this. If we know from the stellar evolution that the density always increases, it's an increasing function, always in this. So density must increase. It increases either here, center, or here.
Yes.
Right. But if the mass is constant, is m or r cubed. And if density increases, radius must decrease for constant mass.
Yes.
And decrease in radius means increase in temperature
Yes.
because of L T4, T to 4, R to square. Decreasing in radius must increase in temperature because the luminosity is always increased because of the fueling, internal fueling. Maybe this is that, I don't know, but my guess was probably. And this relation follows from equating rotational energy of a star and gravitation and thermal energy of a star.
Yes.
So this, but I'm not sure.
Yeah, I think that's one way to. I think there's can be, several ways to understand this behavior. And yeah, this is rapid rotation makes the entire star like a single core. So as it burns, all the star can just simply the density can be increasing as you wrote. this is one way to understand. I think yes. Any other questions?
So, if there are no any urgent questions, so let's send the.
Thank you very much.